Let me try to finish this chapter, okay? And then at the end of the class, let's confirm our midterm exam date. So this is the new section, chapter 4, further issues. What does it mean? So let's recap of where we've been, okay? Remember chapter 3 gave us exact inference under normality, right? So we got a very important assumption, which is normality for chapter 3. And chapter 4.1 here showed us that even without normality, our t-test, f-test still work fine, right? Because asymptotics, which means in large samples, right? And now this chapter, okay, chapter 4.2 is a bit different because it's a calculation of practical issues, okay? We don't have new theory here. Just some practical tricks that you might need when you write your own paper. So things like how to interpret models with logs and quadratics more carefully, how to compare models with different functional forms, and how to do the prediction and other loose ends we've been setting aside until now, okay? So think about this chapter as tools for real-world regression work. Less new theory, more how do I actually use and interpret what I've learned so far, okay? It's about interpretation. Let's go through it slide by slide. Okay, let's talk about logs, when to use them and when not to. So why we love logs? The first 4 points. Okay, the first one, because we can have percentage and elasticity interpretation. We've used this all course, right? Coefficient on log x tells you the percentage change in y for a 1% change in x. This is elasticity, all right? So easy interpret. Next one, invariant to rescaling. What does it mean? It means that whether wage, suppose we have wage, whether wage is measured in dollars or thousands of dollars, log wage coefficient doesn't change, okay? So it's convenient. Units stop mattering, all right? This is invariant to rescaling. Next one, reduces the influence of outliers. What is outliers? Some points that is out of our regression line, those are outliers, okay? So basically, logs can compress large values, so extreme observations don't dominate the regression as much, right? Next point. It often helps normality and homoscedasticity, okay? So we saw this earlier with wages, right? And then we take log on wages, okay? So log on wage looks more bell-shaped than row wages, okay? So this deal with normality and homoscedasticity. Those 4 points are the reasons that the benefits of log, okay? How about when do we not use logs, okay? When should we not use? The first case, if the variables already in natural units, such as years, right? Age, education. Logging years doesn't mean anything useful, okay? Next one, if the variables already in percentage points. If the variable already in percentage points, like interest rate, okay? Interest rate, it's already a percentage. So logging it just makes it confusing. Okay, so this is the interest rate. I use I to represent. Next one. Log don't work on zero or negative numbers. You cannot take log 0. So if a variable can be 0, like hours worked for someone unemployed, you cannot just log it, okay? And the next point, if your model predicts log y, you can't just take exponentiate to get y back. It's not that simple, okay? And there's a correction needed. We'll cover that later. Just remember, predicting y itself is trickier than predicting log y, okay? So let me show you the reason. Should we log your variable and when? Yes, we should. When wages, prices, income, GDP, always positive skewed, okay? For those kind of variables, yes, we should log it. No, like years. Or the variable is already in percentage. And also zeros or negative. Okay, for those kind of variables, we cannot take logs, okay? Let's look at this example. So here we have quadratic functional forms, okay? So the example is the wage equation. We use this when the effect of x is not constant. It means it changes as x gets bigger. I'll show you later. So let's see the example. So here is our regression output. Wage hat equal the intercept plus beta 1 times experience minus beta 2 experience squared. You see here, we have, and look at the sign, we have positive on experience, but negative on experience powered, right? Experience squared. So this shape is called concave or convex. This one, this is concave, right? This is concave. I mean the shape of the function, okay, of the graph. This is concave. Because we have the quadratic term, which is negative, right? That means it slopes down, okay, bends down, which means wage goes up with experience, but slower and slower. Makes sense, right? Your first year of work teaches you a lot. How about your 20th year? Not much new. Okay, so what is the question? When you look at this output, what is the question? The question is, what's the effect of one more year of experience on wage? Okay, this is the question. We can't just read off 0.298. That number alone isn't the real effect. Okay, because experience appears twice in the equation. So here we need calculus. What is calculus? We need calculus. We need to take the derivatives, okay? So let's see here. In order to get the marginal effect of experience, we need the derivative, okay? So delta wage over delta experience. So basically this is beta 1 and minus 2 times beta 2, right? So this is simple. You just take derivative, okay? So what does this mean? Okay, so here it's not one fixed number anymore. It depends on where you are because we have experience variable here, okay? Which means how much experience you already have, right? So let's check with real numbers, okay? Suppose we're going from 0 to 1 year. Rises wage by about $0.3, okay? And how about going from 1 to 2 years? The effect is now, so you plug in 1, okay? In this marginal effect, you get 0.29. Which means, okay, you compare with more experience of working, actually the marginal effect is decreasing, right? From 0.3 to 0.29. So a bit smaller. The key information here is that when you use quadratic functional form, the effect of x changes as x changes. Okay, let me repeat. The effect of x changes as x changes. You always need the derivative to find the real slope at a specific point. Okay, so this row coefficient alone is not the answer. All right, let me show you the graph. Okay, let's look at this graph. So as I told you before, the curve is concave, okay, upside down U. So it has a peak, right? This is the peak point. And how do we find the peak? We need derivative, right? So here we need derivative. X star, okay, equal beta 1 hat over to beta 2 hat. This is we take the derivative and set it to 0. It's like the first order condition, right? You learned from microeconomics. And then you already got the coefficients, right? You copy, okay, from here, the output here, you plug the number in. So the peak point, which means is approximately 24.4 years. The model says wage peaks around 24.4 years of experience, then starting going down. But wait, Does experience really hurt your wage after 24 years? Not necessary, right? Here's why this number can be misleading. Think about what quadratic is. Okay? Basically, we just borrow the quadratic equation from mathematics, right? And then we got this kind of concave shape. And once we fit our regression, which is beta 1 experience plus beta 2 experience squared, this shape is fixed. Okay, the shape is fixed, which means it's a parabola. Okay, this is a parabola. It must turn around and come back down eventually. This is just geometry. Okay, this is just geometry. The model doesn't know anything about careers or labor markets. It's simply the best fitting curve given the data, right? So the model, the fitted model, they are not economists. They don't know how to explain, but you guys know, okay? We just use it as a mathematical tools to find the best fitted line, all right? So a peak and decline don't necessarily mean something real. It's happening in the economy, okay? And also, you see, only about 28% of the observation has more than 24.4 years of experience. That's a small slice, okay? We are trusting the model in a region where we don't have much data. Maybe, okay, it might be the case that we are missing a variable, just like the omitted variable bias, okay? Something else is driving the drop, not experience itself. Okay, let me repeat again. If you use quadratic functional form, don't blindly trust a quadratic curve outside the range where you have lots of data. The turnaround might be real economics, or it might just be the parabola shape forcing itself to bend. Okay, next one, let's see. Next example. This one mixes logs and a quadratic together, okay? Things gets more complicated here. We have log and quadratic together. Okay, so this is the regression output. Okay, here, NOx is the air pollution. Dist is the distance to jobs, okay? Rooms means number of rooms. And this one, ST ratio, is the student-teacher ratio, okay? So I explained it, every variables here. NOx and dist, they are logged, right? They are logged. So their coefficients are elasticity. Simple and easy, which means a 1% increase in air pollution is associated with about 0.902% decrease. Why decrease? Because this is negative in price. Okay, so let's see the room. Rooms in quadratic. We have rooms and rooms squared. Okay, same idea as the wage experience example. So we need to take the derivative to get the marginal effect, right? So here you take delta log price over delta rooms, you got. This is the coefficient for rooms, right? And this is 2 times 0.062. Let me write it down. Okay, so which is 0.124 rooms. Same lesson before, okay? Don't read the linear term alone. We need the real marginal effect, okay? Which is here. This is the real marginal effect. And let's find the turnaround point. So this case, in this case, the curve is convex. Why? Any idea? You see, because here we have log price in terms of rooms. Let's see the coefficient of rooms. This is the linear one, but for the quadratic one, this is positive, right? Positive, which means upward, okay? So we have convex here. And the same idea, we take the first order condition, we can find the minimum point, right? So which is 4.4, which is here. So this curve is convex, U-shaped, not concave like the wage example. Below 4.4 rooms, the effect looks negative, but only 1% of houses have that few rooms. Okay, only 1%. Almost no real house, so we ignore that part. Basically, we ignore this part. And then what matters is the real houses, okay? Let's see, from 5 to 6 rooms, you plug in 5 here, right? So basically, we can get a positive 0.5%. Where does this come from? It's here, our marginal effect, right? So here, you plug 5. Here, you'll get this number. And then you plug 6 here, you'll get 99.9%, almost 20% price increases, right? So you see the effect grows. One more room matters more once you already have a big house. That could be the jump from a 2-bedroom to a 3-bedroom home, okay? Again, with quadratic, the marginal effects can even change direction, right? Depends on the quadratic term, positive or negative. Always check the turning point against your real data first. All right, so be careful about the quadratic function form. Next one. Okay, let's see other possibility. What is this? We have log and then log squared, which means quadratic in log logs, right? So this is our regression model. This is not the output, right? Because we don't have the coefficient, not yet. Okay, so here, let's take the derivative, okay? Let's take the derivative, delta log price over delta log NX. Okay, so beta 1 here, and then 2, beta 2. But here is log logs, right? So this is the first order condition. What does it mean? What does it mean here? It means elasticity that changes with the level of logs, okay? I'm going to use epsilon to represent the elasticity. Okay, for for higher polynomials, okay, suppose it go beyond degree 2. So we have cos equal beta 0 plus beta 1 quantity plus beta 2 quantity squared plus beta 3 quantity power 3 plus mu for this kind of higher polynomial. So this case, the cos function here, which is cubic, right? And it's common for cos functions, okay? Always allowing more flexible ace-shaped curve. Same rule either way, okay? You take derivative and then you'll get the marginal effect depends on x. Okay, here is the rule. Take the derivative and then you'll get the marginal effects. Okay, let's think about it. When should you use quadratic or higher polynomial? When should you? You cannot just take the quadratic as you want. Okay, the example that I showed you before. Suppose you are doing the maybe this is more realistic, okay? Think about cost minimization. Okay, this is cost minimization, right? That's why we need to find the minimum point. Okay, so for this case, it might be optimize maximum utility for those kind of thing, okay? So if you want to use quadratic functional form, you need to think about some theory to support your choice, to support your idea. Like the example here, cost function, right? Have you still remember the total cost curve? Something like this, right? This is the total cost. So basically, in order to get a fitted line, we need to use the cubic, right? So this is based on the theory, which is from microeconomics. Next one, let's talk about the interaction. What does it mean, interaction? Look at interaction means instead of a variable interacting with itself, okay, before I showed you rooms and rooms squared, okay, so this is interact with itself, but we are also allowed to interact with other variables, okay, two different variables interact. Say, look at here, this is our regression, okay? So here we have a new variable, which is square feet times bedrooms. What does it mean? This is the interaction term. So this term means that the effect of bedrooms depend on the size of the house. Does it make sense? The effect of the bedroom depends on the size of the house, right? And then we take the derivative, delta price over delta bedrooms, you'll get beta 2 here and plus beta 3 square root, right? So this new term and the effect of the number of bedrooms depends on the level of square footage, okay, which is the size. So the same idea as quadratics, okay? The effect isn't one fixed number. It depends on another variable now, instead of on itself, okay? So the warning showed you beta 2, you see, beta 2 alone is the effect of one more bedrooms on only one square root equals 0. No house has 0 square footage, right? No house has 0 square footage. So beta 2 by itself means nothing here. Okay, effect on number of bedrooms, but for a square footage of 0. This is not realistic. So you need to question about this. Beta 2 alone means nothing. Again, if you want to use the interaction term, you let one variable's effect depend on another, but just like quadratics, okay, don't read the standalone coefficient. Always plug in a realistic value for the other variable. You need take derivative and then plug a realistic number to get the marginal effect, right? So this is a new trick to fix last side's problem, reparameterization. Okay, so this is our original model. You see y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2. So here is the interaction, right? x1 and x2. So how do we solve it? We rewrite it. How to rewrite it? We center x1 and x2 at their means. All right, so here y equal alpha 0 plus delta 1 x1 plus delta 2 x2 plus beta 3 x1 minus mu1 times x2 minus mu2. What is mu1, mu2 here? Mu1, mu2 is the population mean of x and x2 respectively, but we can replace it by sample mean, right? Because population mean is always not available. So right now, let's see, delta 2 has a clean meaning, the effect of x2 if all variables take on their mean values, okay? So here, in other words, right now, delta 2 means the effect of x2 at the mean of x1. Okay, be careful, mu1, mu2. Here is not the error term. Here is the sample mean of x1 and x2, okay? So here is the advantages of reparameterization. Why we need it? Why bother? Basically, there are 3 advantages. The first one, easy interpretation. Because every coefficient now means something real. And then stand errors for partial effects as the mean values available. So we can get it from the regression output directly because this regression output gives you SE of delta 2, right? automatically. You don't need to calculate. And then we can use our t-test, right? Because this is the single univariate testing. So we can use our t-test to test the effect at the mean directly. Next one, flexible centering. If necessary, interaction may be centered at other interesting value. So here I showed you that I center it at their means, right? But actually you can choose, or maybe the median. So it's flexible, okay? Maybe medium, maybe a policy cutoff, whatever fits your equation, you can center it. This is the same trick from chapter 3. Relabel variables. So the coefficient you actually want pops out directly, right? So with its standard errors included. Okay, so my question is, until now, how many functional forms we covered? Can you recall it? I'll give you several minutes. Functional form. How many functional forms that we just covered? Quadratic, and log, and then log in quadratics. What else? Give you a chance. What else that we covered? Any other functional form that I didn't mention? Interaction. I'm not sure will you use those kind of functional form for your paper or not. Okay, so let's continue. This one, average partial effects. What does it mean? Okay, so look at here. In model with quadratics, interactions, and other nonlinear functional forms, the partial effect depends on the value of one or more explanatory variables. What does it mean? It means that with quadratics or interactions, the partial effect isn't one number, right, that I showed you before. It depends on another variable. So it depends on x. How do we report one summary number? Okay, the question is, how do we report one summary number? The solution is, okay, what is the solution? The solution is here, average partial effect, which is APE, is a summary measure to describe the relationship between dependent variable and each explanatory variable. So what is the idea? Basically, we compute the partial effect for each observation in the sample. The first step, compute. Okay, we compute the partial effect for each observation in the sample, and then we use their own actual x values All right, then we average across everyone. Two steps, all right? So first we compute the partial effect and then we average. This single average number is the APE, which is the convenient summary of the typical effect across the whole sample, even when the true effect varies person to person. It doesn't matter, right? The true effect always varies person to person, but the average partial effect is the single number, okay? It's the single average number. New section, okay? Let's take a closer look at R squared. Remember, we use R squared to measure the goodness of fit, right? By R squared. Okay, so here are two key warnings. First, a higher R squared does not imply that there is a causal interpretation. I think I mentioned this one to you many times. A higher R squared does not imply that a causal interpretation. And right now, it's very difficult to do the causality. So basically, we are doing the correlation. Okay, it's correlation, not causality. And the other way around, a low R squared does not preclude precise estimate of partial effects. What does it mean? Lower R squared doesn't mean your estimates are bad. Okay, be careful. You might say it in your exam. So you can still have a precise, meaningful beta j hat even if R squared is small. Because R squared is about overall fit, not about whether this specific coefficient is well estimated, right? So now, what is R squared actually estimating? Look at this formula. Okay, this is the ordinary R squared. What is the formula? 1 minus SSR over SST, right? And then we arrange it, 1 minus SSR over N and SST over N. Why? Because this sample formula is estimating a population quantity, which is 1 minus sigma mu squared over sigma y squared. Okay? So this is the population R squared. In words, it means R squared estimates the share of variation in Y that's not explained by the error term mu. Okay, let me write it down. Okay, R squared estimates the share of variation in Y that's not explained by the error term mu. For example, the share explained by our X at the population level. Okay, so let's continue. Problem with ordinary R squared. Okay, so this one is ordinary r squared. We divide it by n instead of the correct degrees of freedom. Makes it slightly biased. All right, so this one is a little biased. If it's biased, the problem is that how we fix it. Because here, we divide it by n, right? For the ordinary r squared, we divide it by n. But actually, as I told you before, we need to correct it by the degree of freedom. Okay, so let's see here. That's why we have our adjusted r squared, a better estimate taking into account degrees of freedom. You see? So in this case, there's r squared bar. This is adjusted r squared, okay? So we have new family here. This is original r squared. This is adjusted r squared. So let's look at the formula. Nothing changed here, only one thing. Instead of dividing by n, we divide it by the degree of freedom. Okay, n minus k minus 1 for SSR, and for SST, it's n minus 1. So this is the correct degrees of freedom of numerator and denominator. And this is adjusted r squared. What is the property? The adjusted r squared imposes a penalty for adding new regressors. We have a penalty here. Because for ordinary r squared, if you put more x in your model, the r squared will increase for sure, right? Because more x can explain better y. But instead, adjusted r squared imposes a penalty. If that x doesn't help, okay, if that x doesn't help, it will not increase. And then the adjusted r squared increases if and only if the t ratio of a newly added regressor is greater than 1 in absolute value. Which means if only and if the new added x is significant influence y, the adjusted r squared will increase. Okay, so let's compare. Ordinary r squared always goes up when you're adding anything, but adjusted r squared, actually, it can go down. Be careful, it can go down. So let me write it here. Adjusted r squared increases if and only if the new variable's t ratio has t absolute, which is greater than 1. Okay, this is the necessary and important reasons. Okay, add a newly useless variable, adjusted r squared actually false. So let's see the relationship between normal r squared and adjusted r squared. Adjusted r squared equal 1 minus 1 minus r squared, okay, times n minus 1 over n minus k minus 1. So those are the correction by the degree of freedom, right? The adjusted r squared may even get negative. Look at this formula and think about why. I'll give you several minutes. After this, I'm going to show you with one example that adjusted r squared can be negative. Look at this formula, please, and here. So this is ordinary r squared. What is the range? It's between 0 and 1, right? And for adjusted r squared, there's a bar, and it can go negative. y. Okay, so think about, suppose you have n equal 20, which means you have 20 observations. How about your k? Let's see. What is k? K is the number of x, right? Your explanatory variable. So suppose we have k equal 15. 15 regressors. That means compared with your observation, the regressors are way too many. And suppose we have r squared. This is the ordinary, okay, which is 0.3. Means model barely fits. Okay, so can you compute the adjusted r squared for me? Use that formula. I'll give you 2 minutes. You plug in numbers, right? You plug in numbers, r squared. What is n? What is n? What is k? And then tell me what is your adjusted r squared. What is your answer? Negative. Louder. Negative 2.325, right? Okay, so let me show you. 1 minus 0.3, you time 20 minus 1 in the numerator and 20 minus 15 minus 1 in the denominator. 1 minus 0.7 times 19 over 4, which is 1 minus, which is negative 2.325. So we have a negative adjusted r squared. What does it mean? What does it mean? Okay, let me help you. For simple linear regression, y equal beta 0 plus beta 1x plus mu. This is our simple linear regression, right? So if no x, if we don't have any regressor, what does it mean? If no x, y equal beta 0. So actually, this is the average effect of y, right? This is the average effect of y, which is represented by the intercept. Okay, so if you add too many x but your adjusted r squared is negative, That means the x that you added in your model doesn't help explain y at all. Right? Okay, let me repeat. A model with no regressor at all has r squared equal 0, right? If no regressor, y equal beta 0 and r squared equal 0. So a negative adjusted r squared means your model, despite having 15 regressor, fits worse than just using the sample mean to predict everything. Okay? So the key point is that adjusted r squared can go negative when you cram in too many useless variables related to your sample size. Okay, let me write it down. And it's a warning sign of a badly overfit model. Okay, so today I'm gonna only cover up to this page. Let me explain this to you. Think about when you are assigned to do the group work. Okay, maybe another question. The midterm is coming. How would you study for your midterm? You study alone or you study with your friends? Okay, so can you see, most of you can study alone very well. On the contrary, if you study with your friends, like you put another x in your model, that x doesn't help you to get a better score. Okay, so this is the difference. And I think I have how many? I have 6 pages left. 6 pages left. I think I'm gonna send you a video recording. Okay, maybe just 30 minutes. I'm done for today. And next class, after, I think I'm gonna talk about the midterm exam. Okay, what is the thing that you should emphasize? So first of all, of course, you need to emphasize on the numerical calculation of OLS. Okay, I checked some of your homework. Some of you use the summation method, but actually you should use, it's better to use the matrix formula, okay? Use the matrix formula. So first one, let me tell you, there are 70 points because it counts at 35%, right? So 70 points. There are 30 multiple choice questions, like I showed you in Kahoot. So I'm gonna have Kahoot later because we only had Kahoot for chapter 1, right? So 30 multiple choice questions, it's about Kahoot. And we have 40 points, which is the short answer question. And for 40 short answer question, there are 4 ground questions. So for each ground question, we have sub questions. You can imagine, right? We have 4 chapters. So each chapter gonna have 1 short answer question. And you should focus on chapter 2, multiple regression, and also chapter 3, inference. Of course, I'm gonna let you calculate the matrix of OLS for sure, and also how to do the T ratio, F test, and confidence interval, similar as your homework. If you done it by yourself with your own effort, you should be okay. Okay, another thing is that let's confirm your midterm exam date. So we confirmed before, when is it? 24th of August. Right? I posted on Canvas. Anyone has a time conflict? Please raise your hand. Only one? Really? Okay. How about we move to other time session? The same date, 24th of August. How about 3:30 to 6:30? Please check your exam schedule. Please check your exam schedule. Okay, the same day, but we move to 3:30 to 6:30. Check your time schedule. 3:30 to 6:30. Okay. 3:30 to 6:30. It's fine. How about you? So, if no question, I'll see you on Thursday. Bye bye. Thank you. Thanks for coming. So let me reply.